All right, class, let's take a look at some examples, superposition, and also um, finding the Thevenin equivalent circuit. So I got four examples, two of which I'm going to talk about superposition, and the last two we'll get into some examples for Thevenin. All right, so for this first example, it says find the currents and the voltages through and across each resistor respectively. All right, so whenever you're approaching a circuit like this, where you have two or more sources, the method of superposition was created to simplify the analysis for to determine the effects each source will have on a particular resistor. And so it's kind of a long process, but it simplifies the analysis greatly. So basically, what you want to start off with is that you just pick a source you want to start with. So like for example, in this case right here, I decided to start with this source right here, which is the source that's on the right side of the circuit, and eliminating the source that is on the right side. And so how you eliminate a voltage source is that you just replace it with just a simple short. So you short out the voltage sources. And later we'll see an example where we have a current source. A current source is a source that is supplying current to the circuit. Now these circuits and the ones we have been dealing with in the past were voltage sources. So the source is supplying a voltage to the current to the circuit. And so how you eliminate a current source is you replace it with an open. So to get rid of a voltage source, you replace it with a short. You short it out. To get rid of a current source, you replace it with an open. All right, so for this particular example, we have two voltage sources. And like I've stated before, I decided to start with analyzing the circuit with just only the voltage source that is on the right, that's on the left side of the circuit. All right, so to start, all you do is just eliminate the voltage source that's on the right side, replace it with a short. That's what I've done right here. And all you're trying to do is determine the current that is flowing through each resistor with just only the 12-volt voltage source. And so from here, I mean, this is just a simple parallel circuit. You can just do a simple Ohm's law. We know the voltage across each resistor, which is the 12 volts. And we just do a simple Ohm's law. But there's a couple key things that you need to note whenever you are doing this. And this is just my method of doing it, is you want to label your current source, your currents that's flowing through each resistor accordingly. And make note of the direction that the current is flowing in. So we always want to assume that the current is flowing from negative to positive, meaning that the current is flowing in this direction. Come to this junction point right here. We're gonna call this I prime that's flowing down, and then the current that's flowing in this direction through R2, we're gonna call this I2 prime. Okay. And the reason being is because the direction of the current source, the currents that's flowing through each resistor respectively, is going to matter at the very end whenever we are adding the two currents that we found with respect to the voltage source that we're going to be working with. All right, so in this case right here, like I said before, all we have to do is just do a simple Ohm's law. So I1 prime is equal to VR1 prime divided by R1, which is 12 volts divided by 2.2 kilo ohms. And what I calculated is 5.45 milliamps. And notice I put this arrow going down because that's the direction of the current that's flowing through R1 is flowing in. It's flowing down. All right, so for I2 prime, just do the same thing. Ohm's law, 12 volts divided by 3.3 kilo ohms. And I could have decided to say that the current is flowing like this, and that way the direction of current will be flowing. But the key thing here is if you want to use the arrow, you just want to be consistent. So, and you'll see that on the next variation of this circuit. All right, so now this circuit right here is analyzing the circuit with just only the voltage source that's on the right side, the 24 volts. And so just like we did before, what we did was we eliminate the voltage source, the other voltage source, by replacing it with a short. And that's exactly what I did right here. I just replaced it with a short. But in this particular case, is something does something else. By shorting out the voltage source on the left, it also shorts out the resistor. Because what happens is when current is flowing from negative to positive, so right here we have negative on top, positive on bottom, so that means the current is flowing in this direction. It comes here to this junction point, right? And it takes the path of the least resistance. And we all know that whenever you have a short, majority of all of the current is going to flow in this direction right here of the short. So then therefore no current will be flowing through R1. In a sense, we can just go ahead and redraw the circuit without it, just like I've done down here. So I'll call this one 2 prime because this is going to be a variation of 2, circuit 2. All right, so and notice how I kept I2 in the same place. And that's what I mean by keeping your currents in indicators in the same place, because it's going to help you out in the end. All right, so for this circuit right here, it's just a simple 24 volts voltage source in parallel with a resistor. And you just do Ohm's law. I2 prime is VR2 divided by R2, which is 24 volts, divided by 3.3 kilo ohms. And I get 7.27 milliamps. And I'm saying that current is flowing in the downward direction right here. And so now we've analyzed the circuit. We analyzed this circuit with respect to each voltage source. And so all we have to do at the very end is just add the currents from what we found from each circuit that we analyzed. So for I1 equals I1 prime plus I1 double prime. And so therefore, we saw that I1 prime is 5.45 milliamps and I1 double prime is 0. And the reason why it's 0 is because there's no current flowing in this direction because of this short right here. So therefore, I1 is going to equal 5.45 milliamps. I2 equals I2 prime plus I2 double prime. And this is where, this is where it's important to make sure that you have the current indicators in the right directions. The current flow indicators in the right direction. So when we go back up to I2 prime, I2 prime is right here, 3.64 milliamps, which is flowing down. And I2 double prime is 7.27 milliamps, and it also flowing down. So we can just add those two together. If one of these currents that we have calculated or analyzed was flowing in the opposite direction, then we would subtract, right? We would subtract. So therefore, I1 equals 5.45 milliamps. I2 equals 10.91 milliamps. And of course, if you want to find the voltage across each resistor, you can just do a simple Ohm's law. And here's the multi-sim circuit that kind of verifies the calculations. So you got I1 at 5.45, and then the I2 is 10.909 or 10.91 milliamps. All right, so let's take a look at our second example for superposition. And so this time we have a current source and also a voltage source. And so what I've decided to do was start with the current source. So if, like we've done before, we want to eliminate the voltage source by replacing it with a short, like I've done down here in circuit 1. And so notice how I am placing the directions of the current flow. So current is going to flow down until it gets to this point right here. Then some current is going to flow in this direction, and some current is going to flow in this direction and meet back up at this junction point right here and flow in this direction. So to find I1 prime and I2 prime, let's start with I1 prime. All you really have to do is just do a current divider, because we know the current that's flowing into a parallel combination of resistors. And I'm using the two resistor method current divider. And so what I calculated was 600 milliamps, and I put the current flow direction as going up. All right, so I2 prime, I just did a simple KCL. I could have done another current divider, but I just did a KCL because I know the current coming in I know one, the current that's going out. If I subtract the current going out from the current that's coming in, I can determine the current that's flowing in the other branch, which turns out to be 400 milliamps. And of course, and also I'm putting the current direction that's going up. I3 prime, both branch currents are going to meet back up at this junction point right here and flow in this direction. So therefore, I have 1 amp flowing in the left direction. All right, so that's it for the current source. So now let's look at the voltage source. And so what we want to do is we want to replace the current source with an open. And so therefore, this is what your circuit should look like. And so we always want to assume current is flowing from negative to positive. So therefore, the current will be flowing from negative up in this direction, come to this junction point right here. Some current will flow down. And at this point, you may think some current is flowing in this direction. But however, because we have opened up this circuit right here, open up the current source, this current source is acting as like an infinite resistance, blocking all the current from flowing in this direction right here. So therefore, it's kind of like this part of the circuit is not really even here. And so therefore, we can redraw it to look like this, where current is flowing from negative to positive in this direction in a counterclockwise fashion. And actually, we can use the circle down here to perform our analysis. So as you can see, we have a voltage source that's in parallel with two resistors, R1 and R2, in series. And so we can just do a Ohm's law. And because these two resistors are in series, they're going to share the same current, right? So really what we're calculating is the total current. So I've said I1 double prime is equal to I2 double prime, which is equal to your 24 volts divided by your R1 plus your R2. And so I broke them down separately so that we can kind of be consistent on the direction of the current flow in terms of whether or not if we need to add or subtract. So I wanted to keep that distinction. But looking at it, I mean, the current is flowing all in the same direction. It's all going to be flowing in a counterclockwise method. But I wanted to indicate it just so that for the purpose of superposition, so that whenever we get to the very end, we'll know if we need to add or subtract. And so that's really what these arrows are helping out with. All right, and so for I3 double prime, will come back up here, like we said, that no current is going to flow in this direction. So I3 double prime is 0. All right, so now we've done analyzing the circuit with just only the voltage source. So now let's add our currents together. So for I1 is equal to I1 prime plus I1 double prime. And we look at I1, which is I1 prime, which is 600 milliamps flowing up. Okay. And I1 double prime is 4.36 milliamps flowing down. So therefore, we're going to have to subtract. And so basically, what you want to do is you just want to subtract the larger current from the smaller one. And the direction of current flow is going to flow in the direction of whichever current that you calculated direction. So in this case right here, the 600 milliamps was flowing up. So therefore, I1 is going to also flow up. So we come back up here to our original circuit and draw in I1. It's going to be flowing in this direction right there. All right, so now what about I2? So I2 equals I2 prime plus I2 double prime. All right, so I2 prime is 400 milliamps flowing up. I2 double prime is 4.36 milliamps flowing up. So therefore, they're flowing in both the same direction. So we're just going to add them together. All right, and then I3 is equals I3 prime plus I3 double prime. And that's just 1 amp plus 0 because we didn't have any current flowing whenever we were just analyzing the 24 volts voltage source. And so that equals 1 amp. And I didn't do it on this one, but to calculate the voltage, all you do is just a simple Ohm's law because you know the current, you know the volt, you know the resistance. And so just do a Ohm's law and you determine the voltage across each resistor. All right. So this is our first Thevenin's example. And so for this particular one, is you have a Thevenin, you're asked to determine the Thevenin equivalent circuit across R, which is this resistor right here. And you have a current source. And so to find the Thevenin equivalent circuit, you have to follow these steps. Some of the steps are interchangeably, but we'll just walk through them step by step. So let's take a step back. So Thevenin, the reason why Thevenin is important because you may be given like a project, right? Where you're asked to you're asked to develop a circuit that produces a certain amount of resistance and voltage, and basically you're given you know, this is your load right here, and they don't really care what's inside this black box. Right, we don't really care what's in the black box, as long as this load is seeing a particular resistance and voltage, and that's what Thevenin analysis is doing. So the first step that I like to do is I like to go ahead and remove your load resistor, which is right here, and redraw the circuit. So just redraw it, like for like, just without the resistor, just like I've done over here. All right, and so the next thing you want to do, you want to replace your sources and find R Thevenin. So what I mean by replacing your sources, you just want to get rid of them. And just like we talked about in your superposition, you want to replace your current sources with an open and your voltage sources with a short. So in this case, we have a current source, so you want to replace it with an open right here. All right. And so just imagine that you are putting an ohm meter right here, and you're measuring the resistance. So ask yourself, is the ohm meter gonna read this resistance right here? No, it's not, because it's not connected to the rest of the circuit. You got an open circuit right here. So pretty much you can simplify the circuit to something like this right here. And so if you take your ohm meter and you place it across the open circuit for where the load is going to be, and you measure the resistance, you're only going to be measuring R2 and R3 in series. So therefore, your R Thevenin equals R2 plus R3, which is 3.75 kilo ohms. And so that's all you're doing when you're trying to find R Thevenin is that you are getting rid of your source. If it's a current source, you want to replace it with an open. The voltage source, you want to replace it with a short. And just imagine yourself measuring the resistance across where the load resistor should be. And if you have a resistor that's leading out to an open, just like R1 is doing, this ohm meter right here is not going to see this resistor because it's not even connected to the circuit. It's not connected. All right, so now step 3, you want to bring back your source and determine the voltage seen by the load resistor, which is also known as the Thevenin voltage. So right here, we brought back our current source. And so we're trying to figure out what voltage, if we put a voltmeter right here, what voltage is going to be seen by the load resistor. And so I put a little note right here. So you may be kind of confused about, what do we do about this R2? Is it in series or is it in parallel? I mean, it's connected to this open circuit right here. So I'm not really sure what to do with it. But I put a note right here. So no current will flow through R2 because by removing R, which is the load resistor, it creates an open circuit, and the voltage seen by R is really the voltage across R3. Because think about it, current is going to flow in this direction right here. It has an open circuit right here. It has an open. This is open. So no current is going to flow in this direction. No current is going to flow in this direction. It's all going to flow straight through R3. And so therefore you can simplify your circuit like such, where you just pretty much, you can just get rid of R2. And so really what you have here is a current source and 2 series resistors. And all you have to do is find the voltage across R3, which is pretty straightforward. Just simple Ohm's law equation. So your V Thevenin is equal to I times R3, which is 5 milliamps times 2.2 kilo ohms, which equals to 11 volts. And so those are the 3 steps. The last steps is just to put it all together. And so whenever you're trying to find a Thevenin equivalent circuit, you want to put your Thevenin resistance in series with your load resistor. All right. And then your voltage source is going to equal 11 volts. That's your Thevenin voltage. And so basically, this right here, this is your black box. That's your black box right there. So that's the equivalent. This right here, this voltage and this resistance, the V Thevenin and R Thevenin, is the equivalent of everything that's right here inside that black box. And that's pretty much it for that example. And let me think. I don't think I have anything else to say about this one, but yeah, that's pretty much it. That's all you do. It's just 3 to 4 simple steps. You want to start by removing your load resistor, redrawing your circuit, and then you want to replace all your sources with either a short or an open. That's step 2 to find your R Thevenin. So that's one key part, and then you want to find your V Thevenin. Now let's say, for example, that there was a resistor right here, right? Let's call that R4. Well, your V Thevenin will be the voltage that's across R4, right? So you can't, in this particular case right here, you can't get rid of R2 like what we've done before. It's just only because R2 is connected to this, it's not doing anything. It's just connected to an open circuit. And so therefore you can simplify it by just simply removing it. All right. All right, so let's take a look at the last example. All right, so this is another Thevenin. And so this time we have a voltage source. And so just like last time, the first step you want to do is you want to remove the load resistor R. But whatever load resistor you have, you just want to remove it, redraw the circuit. And so this is what it should look like. Step 2, you want to replace your sources and find R Thevenin. And of course, you want to replace any current sources with an open and any voltage source with a short. In this case, we have a voltage source, so you want to replace it with a short. And so just imagine yourself putting a ohm meter at these two terminals right here and measuring the the total resistance. And so what you should see is that this resistor right here is in parallel so R1 is in parallel with R3. So you can add those two together up in parallel. And once you combine these two in parallel, you'll see that the parallel combination of R1 and R3 is in series with R2. So this is your parallel two resistor method, product over the sum. And then you just want to add an R2. So I have 1 kilo ohm times 1 kilo ohm divided by 1 kilo ohm plus 1 kilo ohm plus 1.5 kilo ohm. And I get your total, your R Thevenin resistance is 2 kilo ohms. All right, so for step 3, you want to bring back your source and determine the voltage seen by the load, and it's essentially kind of similar to what we did before. So no current. So if you imagine yourself taking a voltmeter and you're measuring the voltage at the two terminals, the voltmeter is not going to read anything from R2 because R2 it's not going to have any current flowing through it. So pretty much it's just not even there. You can just replace it, take it out, and replace it with a line. And so the voltage that you're actually going to be reading, if you measure the voltage from these two terminals, is the voltage across R3. And so from there, you can just do a voltage divider, which I've done right here. And so so V Thevenin is 6 volts. And to redraw your circuit, the Thevenin equivalent circuit, you have your 6 volts, your R Thevenin, and then your load, you bring back in your load resistance. And just to look at this a little deeper, I redone the whole circuit in multi-sim. So this is your original circuit that we started out with, and if we measure the voltages across our load resistance, we get 3.73 or 3.74. And if we take the equivalence of what's on the left side of the load resistance, and you take the voltage across it, you get the same voltage. So therefore, this voltage source and this resistance is the equivalent of everything that's right here inside this black box. And so that's it for this example. And hopefully this was beneficial to your understanding of this topic. If you still have any questions, feel free to reach out to me. But that's gonna be it for this example. Thank you.